Hello students, today we are going to discuss the mechanism of the nucleophilic substitution reaction. See, here there's the substitution reaction. What actually happens in the substitution reaction? In this substitution reaction, an atom or the group is replaced by some other atom or group. See here, one atom or group is replaced by some other atom or group. So this type of reactions are known as substitution reaction. Now, these substitution reactions are of two types. One, it is electrophilic substitution reaction, while the another one is nucleophilic substitution reaction. See, what are the electrophilic substitution reaction? Here, if the electrophile this replaces the atom or group, that one is called electrophilic substitution reaction, as we discussed in case of the benzene. See, here there's the benzene ring, and when it is treated with the CS3Cl in presence of anhydrous AlCl3, see here what happens. The CS3 plus electrophile replaces the hydrogen of the ring, and we obtains a methyl benzene or toluene, and the H plus or H hydrogen, which will be replaced from the ring, combines to the Cl minus and HCl. This one is an example of the electrophilic substitution. Here this electrophile replaces the atom or group. On the other hand, in nucleophilic substitution reaction, here the nucleophile this replaces the atom or group. See, suppose it is a CH3X and this reacts with the KOH. The KOH will dissociate and forms K plus OH minus. Here in the CH3X, the CX bond is the polar bond. Now, here the bond dissociation occurs, and this OH minus replaces this X minus, and we obtains here OH along with, now the X minus comes out with the K and we'll get KX. Here this nucleophile is removing a X atom, and that's why this one is an example of the nucleophilic substitution. So today we are going to discuss the mechanism of the nucleophilic substitution reaction. See here, this nucleophilic substitution reaction. You may also call it that is SN reaction. Here S stands for substitution and N stands for the nucleophilic, that is SN reactions. So there are the two mechanisms which are proposed for the nucleophilic substitution reaction. One of the mechanism is unimolecular nucleophilic substitution, and the another mechanism is known as bimolecular nucleophilic substitution. The two mechanisms here, the two mechanisms are there for nucleophilic substitution reaction. This unimolecular nucleophilic substitution, you may call that these are the SN1, as the molecularity is 1, that's why it is SN1 reactions. And here it is bimolecular nucleophilic substitution, means that is these are the SN2 reaction or SN2 mechanism. Same way here there are two mechanisms, one is SN1 and one is SN2. So our today's topic is SN1 mechanism. Here it is unimolecular nucleophilic substitution reaction mechanism. Okay. See. Firstly, I am writing here nucleophilic substitution reaction. Let the nucleophilic substitution means SN reaction is CH3C, CH3, here also CH3, and that's the I. This one is our alkyl halide, and here it is our OH minus. This one is acting as a nucleophile. As you know, the nucleophile is what? It is the electron rich species. So, and this alkyl halide is acting as a substrate molecule. In this substrate molecule, the atom or group which is to be replaced, means as here in this case we have to remove this I. So this one is called what? Leaving group. Now in this case, this leaving group will be replaced by the nucleophile, and see, the OH minus means nucleophile is replacing the leaving group. So that's why this one is an example of the SN or nucleophilic substitution reaction. Now this I minus will set free. If here I am taking KOH, so the K plus will form bond with the I minus, we will get the Ki. This one is our nucleophilic substitution reaction example. Now we will discuss its SN1 mechanism. Okay. So what happens in SN1 mechanism, or we can say that the mechanism of, here we are discussing the unimolecular nucleophilic substitution, or we can say that is SN1 mechanism. So what happens in SN1 mechanism? So by taking the example of this reaction, we'll discuss the mechanism of the SN1 mechanism. We'll discuss SN1 mechanism. Here what happens, this SN1 mechanism, this occurs in two steps. It occurs in two steps. What happens in step 1? In step 1, this involves here generation of a carbonium ion, or we may call it, this involves generation of carbocation. What actually happens here? This was our CS3C, CS3, CS3 and I. This is our substrate molecule. And here, as we know that there's the difference in the electronegativities of the carbon in halogen. So here heterolytic breaking occurs and this halogen sets free in the form of the halide ion, along with the, by taking both the electrons of the both the shared pair of electrons. So as a result, what will happen here? The carbon of CX bond has lost its electron, so will become electropositive, will become a positive charged, and this I will set free as a iodide ion. In this way, here we will get a carbocation, or we may call it a carbonium ion. See, I am taking here iodide as a leaving group. This is because the leaving ability of the halide ions of halogens follows the trend that I minus is the best leaving group. Is it clear? That's why I'm taking here I as a this one. This I group is being replaced. So that's why this one is a leaving group. Okay. And here we will get the carbonium ion. Now, thereafter in step 2, the carbonyl which is formed as an intermediate will be attacked by the nucleophile. See here, the second step, this involves attack of nucleophile over carbonyl. Now what happens here? There is this is carbon, here it is CH3, CH3 and CH3. See, in the carbonyl you will find that this positively charged carbon has formed the 3 sigma bonds. It means in this carbonyl ion, the charged carbon remains sp2 hybridized. And if it is sp2 hybridized, so therefore the carbonyl ion, this carbonyl ion will have a trigonal planar geometry. So this one is the, here these 3 all are lying in a same plane, is having a trigonal planar geometry. Now the nucleophile is OH minus. Now this nucleophile will attack over the carbonyl ion. Now see here, in as it is having a trigonal planar geometry, so all the angles are of 120 degree. So this OH minus ion may attack from the front side, as well as at the same time it may attack from the back side or from this side. Is it clear? So what happens here? Here the finally here the CH this OH group forms bond with the OH. C plus group means carbocation forms bond with the OH, and we will get the end substituted product. Is it clear? This one is the mechanism. Now see here, as we know that this reaction occurs in the 2 steps. In step second, the reaction occurs between the 2 ions, oppositely charged ions, positively charged carbonyl ion and negatively charged nucleophile. And we know that the ionic reactions are very fast. So this one is the fast step. While here this formation of the carbonyl ion, step 1, in which the carbonyl ion generation is there. So this one is a molecular reaction, and remember the molecular reactions are slower reactions. So here this one is the slow step or slower step, and always remember the slower step is the rate determining step, and as this step is the slower, that's why this one will be the rate determining step. Means the rate of the reaction will be determined with the slowest step, means with the step 1. And now as we know, according to the law of mass action, the rate of reaction is proportional to the molar concentration of the reactants. So here in step 1, the reactant is our substrate molecule, means alkyl halide. And as we here in the balanced equation, I am taking 1 mole of the alkyl halide. So for the reaction, the rate equation, or you may call that rate expression, can be written as that the rate will be proportional to the concentration of our reactants concentration. See here, as only 1 mole is taken, so here there will be a power of 1. As per the law of mass action, the rate of reaction will remains proportional to the molar concentration of the reactants and raised over some power equal to the stoichiometric coefficient. And here the stoichiometric coefficient is 1, that's why is 1. So this can be written as, see, when we will remove this proportionality sign, we will get a constant, and the same rate expression can be written as power 1. See, as we know in chemical kinetics, it is discussed that the sum of powers raised over concentration in rate equation is called molecularity. So here the molecularity will be 1, and hence therefore the reaction, hence this reaction is called, it is called unimolecular nucleophilic substitution reaction. That is SN. S stands for substitution, N stands for nucleophilic, and 1 means here the molecularity is 1, SN1 reaction. Is it clear? Now see here, there's the one important point here I would like to discuss in this video. That one is, actually for nucleophilic substitution reaction there are 2 mechanisms. One is SN1, one is SN2. See what happens in SN2, always inversion in configuration takes place, while in SN1 mechanism here a racemization takes place. Means we may write a statement that this SN1 reaction or mechanism, this proceeds with racemization. As we know in optical isomerism, there is a term, a racemic mixture. That racemic mixture is the equimolar mixture of the D and L isomers. Means both are having the number of moles of both isomers D and L are in equal quantity. Okay. See here, proceeds the racemic mixture. Means this process with the racemization. Here what happens, here in SN1 mechanism, retention in configuration as well as the inversion in configuration takes place. And why it occurs so? See here, in SN1 mechanism we are getting a carbonium ion as a intermediate, and this carbonium ion is having a trigonal planar geometry. So this OH minus ion may attack from the front side as well as may attack from the back side. there are equal possibilities for attack of OH minus over the nucleophile, and that's why here we may say that here an SN1 reaction proceeds with the racemization. Is it clear?